In this session, we will talk about ADC, that's the analog to digital converter, and we will see the operation of ADC. There are multiple types of ADC, like successive approximation, then sigma delta conversion, and then flash ADC, analog to digital conversion. So we are not going to talk about the different types of ADC. That is not the focus of this session, but rather we will talk about how the conversion happens from an analog to a digital value, and subsequently we will explain a program and we'll write a program, and then we will compile it using KEIL, and subsequently use Proteus to demonstrate the working of an ADC. Now let us talk about the working of an ADC. Now Vin is a voltage that needs to be converted to a digital value, and D0 to D7 are the digital output that are obtained. So in this ADC, analog to digital conversion, we have an analog input that is called as Vin, and we have a digital output that is a D0 to D7. Now how the conversion happens is, Vin is supplied to a comparator, and that comparator will control the counter that is incrementing. Now let us say that I want to start the conversion. At that time, a start conversion pulse is provided to the counter, okay, and subsequently at every clock ticks, the counter is going to get incremented. Now this particular counter output, which is in a digital form, will be fed to a digital to analog converter, which converts the output to a analog form. Okay, now this output of the counter in an analog form is compared with the Vin. If Vin is greater than the counter output, at that time the counter will be incremented again, okay, further. Okay, when the counter output exceeds Vin, at that time we can say that the output of the counter is approximately equal to Vin. When it exceeds Vin, at that time the comparator will go low, the comparator output will go low, and then it will stop the counter from further incrementing. Okay, and at the same time the output of the comparator will also signal end of conversion to successive stage to fetch the value to the microcontroller. Okay, so let me explain again. Vin is the analog value that is supposed to be converted to a digital value. The digital values are here below. They are D0 to D7. Now whenever you want to start the conversion, you will send across the start pulse to the counter. Okay, so initially the value is 0. Okay, at that time what happens is, since the values of digital values are all 0, the output of the DAC will be 0. Since Vin is greater than 0, it will, if Vin is greater than 0, then it will send an high output, which will enable the counter to count further. Okay, and the counter will start counting for every clock ticks. Okay, and as and when the digital output are provided, they are converted to analog form, and they are frequently compared with Vin. The moment the analog output becomes greater than Vin, this comparator output will go low, and the counter will stop counting further. So the digital value that are output of the counter is equivalent to the digital equivalent to the digital equivalence of the Vin that is being provided. So whatever digital value you have in D0 to D7, they correspond to the Vin, okay, in a digital form. At that time the counter will stop incrementing further because the control signal goes low, and at the same time the end of conversion is encountered. Now let us go to the next slide and see the timing diagram, because this timing diagram becomes a critical factor of analyzing and writing the program for the ADC. Okay, this typical timing diagram corresponds to ADC 0808. Now if you see here, the clocks are being provided to the counter. If you want to start the counter, you have to provide a start pulse. Okay, but before you initiate the start pulse, there is something called as ALE. This will latch the address and decide which analog channels are selected in ADC 0808. Actually, in ADC 0808, there are total number of 8 channels. So if you want to select the first channel, then you have to provide address of 000 for pin number A, B and C, and then you have to latch those address. At that time the channel 1 will be selected. Once the channel 1 is selected, and if you want to convert the analog value to the digital value, you say start conversion, and the moment you start provide the start conversion, the digital counter will start incrementing, and it keeps on incrementing, and it keeps on incrementing, and it compares the analog output of the equivalent analog output that is generated with the Vin. The moment Vin becomes lesser than the digital output, at that time the end of conversion gets signaled. Okay, this end of conversion will signify that the analog value is completely now converted to a digital value, and at that time the counter will stop counting. And further to that, if you want to read the digital output, you have to enable the output and then only read the digital values from the ADC to the microcontroller. So having discussed about this particular waveform, now let us derive the steps for generating the digital from the analog value and interfacing the same thing in the microcontroller. So the first step, if you see, is selection of channel. Okay, so once you select the channel, you need to bring the ALE up and then down. Once you do that, at the same time you will start bringing up the start conversion up and down. So when the start conversion becomes down, the internal the counter starts incrementing. Okay, and it will keep on incrementing till the end of conversion becomes high. Okay, once the end of conversion becomes high, you have to bring the output enable to high and then read the data, and then bring the output enable to low. Okay, so let us see the steps then. Okay, step number 1 is select the channel that you want to get the analog input from. Okay, so this is selected based on the values ABC. If ABC is 0, then the channel 0 will be selected. If ABC is 111, then channel 7 will be selected. Okay, now once the channels are the channel inputs are given, okay, then we have to bring up the ALE. So that's the reason we call it as an assert ALE. At the same time, once you have provided the ALE and then you have latched the channel address, then you will initiate the start conversion. And once the start conversion is initiated, we will wait for the end of conversion, and once the end of conversion is attained, then we will enable the output enable pin and then read the digital values to the appropriate destination. Now, okay, let us explain this circuit. This particular circuit has got ADC and that is interfaced with the microcontroller. Now if you see the ADC, the address A, B and C are mapped to pin port number 3.4, 3.3 and 3.2 respectively. Okay, and the ALE is mapped to port number 3.1, and the P3.0 is mapped to OE, and the start of conversion is mapped to P3.5, and end of conversion is mapped to 3.6. So the way we have to use this is, initially we have to make ABC as 0 so that it selects a channel 1. So if ABC has to be 0, then P3.1, P3.2 and P3.3 should be 0. Okay, I'm sorry, it is P3.2, P3.3 and P3.4 has to be 0. Once they are 0, we will have to lag the address. So that is done by pin number 3.1. So address latching is done by P3.1 and the address provision is done by P3.2 to 3.4. And once we have latched, then we have to start the conversion. That start of conversion is mapped to P3.6, and once the ADC completes the conversion, it will acknowledge using end of conversion. Okay, so the end of conversion will be P3.6, and further, after the end of conversion is received, then we have to read the we have to set OE or assert OE to make the ADC to provide the digital value of the digital equivalent of the analog value through output out1 to out8, and that is received by P2.0 to 2.7. So here, if you see in this particular circuit, the analog input is controlled by the potentiometer, and the digital output provided by the ADC is mapped to out1 to out8, which is received by P2.0 to 2.7 of the microcontroller. Further, the microcontroller will transfer that to P1.0 to 1.7, and the respective LEDs will glow. Now let us focus on the writing the program for this. Okay, so let me open the KEIL session. Okay, so first I will include I'll write a C program. So I say include reg51.h. Now let us see what are the different pins that are mapped. Okay, so let us define that. So S bit ALE. So okay, so we need to define ALE. Okay, so then S bit we have to define CHAN channel A. Okay, so I'll use CHAN underscore A. Okay, then S bit CHAN underscore 2 is equal to S bit CHAN underscore C is equal to underscore C is equal to underscore C is equal to, so this is not 2, channel underscore B is equal to. Okay, now these are the address and latching. Now we have to check which is mapped to start. So I'll say start is equal to, okay, S bit. Then once the start is initiated, we have to read and start and then end of conversion. Okay, so once end of conversion is attained, we have to read output enable. Okay, so let us see what does what pin ALE maps to. Okay, ALE maps to pin number P3.1. P3.1 ALE maps to P3.1. Okay, P3 cap 1. The way the syntax is P3 cap 1. Channel A maps to P3.4. P3 cap 4. Channel B maps to P3 cap 3. P3 cap 3. Okay, channel C maps to P3 cap 2. Okay, now start pin maps to, let us see this, start is here, it maps to P3.5. P3 cap 5, and end of conversion EOC map to P3.6 and OE map to P3.0. Okay, this is P3.6, P3 cap 6, and OE map to P3 cap 0. Okay, so now we have defined all the respective pins Now we will start the main program. Void main void. The first statement that we have to do is we have to set channel A, channel B and channel C to 0 is equal to 0. Then so let me align it here. Okay, so channel CHAN underscore B is equal to 0 and CHAN underscore CHAN underscore C is equal to 0. Okay, fine. Okay, now once we have done that, we have to latch the address, because I am looking for my potentiometer is connected to channel 0. Okay, so I say ALE. So how do I decide on the latching process? If you see, go back here to the PPT. First ALE has to be high, then start has to be asserted high, ALE should be low and start should be low. So I say ALE is equal to 1. Okay, ALE is equal to 1. Then start conversion should be high. Okay, START is equal to 1. Okay, START is equal to 1, ALE is equal to 0 and then start is equal to 0. Okay, so we have simulated this waveform. First you provide the address, then make ALE high, then start high, then ALE low, start low. After you have done the start as low, you have to wait for EOC to become from 1 to 0. So we will wait for EOC to be equal to 1 while, so I say WHILE EOC end of conversion equal to 1, then I will loop. Okay, so it will loop till this particular point, then I have to loop till EOC becomes 1 again. So I'll say while EOC equal to 0, I will loop again. Okay, so now I have come till this point. So once I have reached this point, that means my output, so EOC, while EOC equal to 1 will loop till here, and while EOC equal to 0 will loop till here. Once I have done that, then it's time to make output enable as high. So OE is equal to 1. Okay, once I have done OE is equal to 1, then I'll have to read the ADC data. Okay, so what I'll do is I'll say P1 is equal to, okay, P2. Why I'm saying this? Why I'm saying P1 is equal to P2? Primarily because, sorry, 1 minute. P1 is equal to P2. Why I'm saying is, once I say output enable, the output will come through the ADC and will hit the P2. So I have to read the value of P2 and transfer it to P1. Okay, so P1 is equal to P2. Then I'll say OE is equal to 0. Okay, so because after reading it, I have to make output enable as low. Okay, so that is about the program, and this has to be in a continuous loop. Okay, so I'll say while 1, okay, and then I will close the bracket here. Okay, so there is a small changes that I have to do still further. Okay, so this is the mechanism of reading the ADC. Now here I have to make P1 is equal to 0xFF, that is, okay, sorry, P2 is equal to 0x is equal to 0xFF. That means all the port 2 pins here will be in the read mode, and P1 I am not going to touch it, so it's in the write mode. So then I have to identify which of the pins in port 3 are in read mode, and which of the pins in which of the pins are in read mode, and which of the pins are in write mode. So if you see here, OE is the output enable, so it is a write pin. Okay, P3.1, P3.2, P3.1 is ALE, it is a write pin. P3.2 to P3.4 is channel ABC, they are also write pin. P3.5 is start conversion, it is again a write pin. End of conversion EOC, okay, is the read pin. So this has to be in a read mode. Okay, so let us see. EOC has to be in the read mode, so that is mapped to, EOC is mapped to P3.6. so I'll say P1, okay, P1 is equal to 0x40, okay, P1 is equal to P1 is equal to 0x40. Okay, so let me come back again. OE, output enable, is the write pin. Okay, address latch enable is the write pin. Then ABC, channel ABC are the write pin. Then start is a write pin, whereas end of conversion is a read pin. So this is mapped to 3.6, so it is P3 should be 0x40, so it is not P1, sorry, not P1, it is P3. Okay, okay, let me save this. There's some problem with my KEIL. Let me minimize everything and let me reopen it. Okay, let's see this now. P3 is equal to 0x40. Okay, so that is about the program. So it is in a are we in a while loop? Yes. So let me compile this. Okay, there are no errors. So let me go back to the Proteus and let me burn the file. This ADC, let me confirm whether it is ADC. So it is adc.hex. Okay, so I'll say okay, and now I'll run the simulation. Now let us see what is happening. If you see, the output is 0. Okay, so output is, potentiometer is pointing to 0, so there is no output here, none of the LEDs are glowing. Let me go to maximum value. Okay, so now that it is the maximum value, is it a maximum value? Let me go. Okay, now it is a maximum value, all the LEDs are glowing. So let me also insert a voltage source, so that DC voltmeter, and then measure the voltage. Insert a terminal, ground terminal, and connect the ground terminal to one end of the voltmeter and connect here and here. Okay, now let us run this. Okay, so if you see here, now it is 4.99 volt. For 4.99 volt, I am expecting the output of the ADC to be FF, so all the LEDs are glowing. So if I reduce it to half, that is 2.5, let me do that. Okay, now if you see here, the output of the potentiometer is exactly 2.5. so if you see, I expect it is 7F, so okay, it is matching. Okay, and if I make it 1.25 expect it to be 3f. So let us see if that is happening. 1.25, 1.5, okay, 1.25, 1.25, okay. So increment, let me go here, let me unzoom it, let me stop the simulation, and let me see by what step potentiometer value changes. So is it controllable? No, it is not controllable, so I have to be happy with that. So let me run this, okay. If it is now it is 0.5, 0.5 is okay, so point, let me go further down, 0.0, 0 volt means everything is 0 0, then half, 2.5 is 7f, and finally 5, let us put 5 volts, 5 volt is ff, okay. So let me go back to 4.5, 4.5 corresponds to E5, so that we can calculate it, okay. 1 minute, 4.5 divided by 5 is 9 by 10, okay, it's 0.9, 4.5 divided by, okay, it's 0.9, okay, into 255, so this is equal to 230, okay. So 230 in hexadecimal would be E5, so I'm expecting E5, so I'm getting 1110 so this is E5. So if I go down by another point, my output voltage is 4 divided by 5 into 255 is 0.8 into 255, so it is 0.8 into 255, so this gives you I have to switch to the decimal mode, give me a minute, 0.8 into 255 gives you, so if I convert this to a hexadecimal, it is cc. So let me see whether I am getting that cc. 1100 is c and 1100 is c, so my program is working fine. Let us revisit the ADC in assembly language. So let me go back to the steps that we need to follow, okay. So first thing is we have to select a channel, then we have to assert ALE, then assert start conversion, and then wait for EOC to become high and assert OE. So we'll go back to KEIL and write an assembly program. Let me remove the C file and add a new assembly file. Okay, done. So here I'll say start, so I'll set the different channels parameters. So first what I'll do is I will have to set let me go back to the Proteus, okay. So ABC I'll set it to 1, they map to P2.3, P2. ABC I'll set it to 0, P3.2, P3.3 and P3.4 have to be set to 0. So I'll say CLR P3.2, CLR P3.3, CLR P3.4, okay. So that are set to 0. So now channel 0 is activated, but it is not yet because I have to set ALE to high and low. So I'll say back loop set bit P, the ALE is mapped to p3.1 3.1. okay, so once I have oh man, let me reopen. To the set bit p3.1. okay, then after setting the ALU, let me go back. So we have to make start as high, start conversion as high. So start conversion is mapped to p3.5. so set bit p3.5. okay, once we do that, we have to clear the ALE, as well as we have to clear the start bit. okay, so clear p3.1 CLR p3.5. okay, so then we have to wait till end of conversion becomes 1. How to do that? I say jump on bit EOC within itself, and jump on no bit EOC within itself. Now where is that EOC mapped to? EOC is mapped to p3.6. okay, so you say a loop 1 jump on bit p3.6 loop 1. okay, so it will keep on looping till p3.6 becomes low. p3.6 corresponds to EOC, so it will wait till it becomes low. So this means it will wait till EOC becomes low. So it was initially high, and it will wait till it becomes low. I'll also copy the same thing, and then I'll say jump on no bit. okay, p3.6 loop 2. okay, jump on no bit. So when I say jump on no bit, what it means is it will wait till it becomes 1. okay, jump on no bit. okay, so first we have enabled the ALE, enabled the start, disabled the ALE, and disabled the start. Then we have waited for EOC to become 0. Then we have waited for the EOC to become 1. Once we have received EOC as 1, then we have to say OE. We have to set OE to high. So where is OE mapped to? OE is mapped to p3.0. So we say set bit SET bit OE. So p3.0. then after that, once we have set it, then the output will we enabled, and all the output will be available in port 2. So then we will move that to port 1. So here we say that move a comma p2. okay, move a comma p2, move p1 comma a. okay, so after that you say as jump loop. As jump, shall we say loop or shall we say start? Let's say loop p. okay, I will say start just because the channel may have to be set, but not necessarily. Okay, so here before that what we'll do is we'll introduce one more line. We'll put P1 to read only mode, so we'll say move to the read mode, all the P1 pin, all the P2 pin to the read mode, say P2 comma hash 0 FFH. Now all the P2 pins are in read mode, then ABC at 0, then set ALE to latch this and select channel 1, channel 0, and then set the start of conversion, then clear those things, wait till end of conversion is achieved. Once end of conversion is achieved, enable OE, that output enable, then read from P2 and send it to P1. So that's it, I think. So that's the program. So let us now compile it. Okay, missing in statement, and 11, that is the syntax error. What is the jump on bit? Okay, there is a comma here, missed on the comma, and this is END. Now let us compile this. Okay, good. So ADC is created, ADC hex is created. Let me put that in our Proteus. So adc.hex. Okay, then I'll run this. Okay, so now that all the okay, let me stop this and also put the DC voltmeter. Place DC voltmeter. Okay, and then make the connections for DC voltmeter. One end of the DC voltmeter is connected to the potentiometer output. Terminal, please, terminal, ground, place it here, connect it to here, and one end of the terminal connect to the potentiometer output. Okay, save it. Now run it. Okay, so all are 0 because the potentiometer is in 0th position. Now increase it. So the voltage is 0.5. 0.5 is 1/5 of 1/10 of 5 volts. So let us clear this and put it in the decimal mode. And 1/10 of so if it is 0.5, the full scale range is 5 volts divided by 5. Okay, so that is 1/10 into 255. That is your decimal value. That is that can be the value of the ADC. 25.5 is the value of ADC. Now if I convert this to hexadecimal, it is 19.8. 19 is nothing but 1, and 19.8. okay, so coming back to decimal, so it is 25.5. so I will clear it and say I'll take it as a decimal. 26 is nothing but 1A in hexadecimal. So if you see 0 0 0 1 1 0 1 0, so it is 1A, so it matches. So if I take 2.5, I should get FFFF. Let me check. If you see, whenever I make the changes, the value of the output of the ADC changes. Okay, if I say 2.5, then it is 0 FFFF. So further, if I say 4.5, let me calculate that. For that, it is coming as E5. So 4.5 is coming as E5. Let me verify that. Okay, I'll set decimal mode. Then 4.5 4.5 divided by 5 gives you into maximum range is 255. So I got 229.5. If I convert this to hexadecimal, it is E5. So if I see here E5, it is E and 5. Excellent. Okay, so we have achieved our goal. So this is the assembly program for the same. Okay, so what we are doing, we are setting the port P2 in the read mode, and then we are putting ABC as 000. Why is ABC equal to 000? Because we have to select channel 0. Now if any other channel is selected, then choose ABC appropriately. Okay, then we do the start of conversion, address latch, and then we do the start conversion, then reset address latch as well as reset start of conversion, and wait till end of conversion is reached. Once we get the end of conversion, then we do the output enable and read the digital value. So that is about the assembly program.